All right. So, did you guys look at any of the homework?
Yeah.
Try any of them? Any questions
did.
on what we were doing last time? Because last time was really just sort of the basics, the classification in terms of like the order of the differential equation and that sort of thing.
Yeah.
So we good?
Real quick, I do
Yeah.
have a question. So if, let's say it's not linear, we can still find the order, or we just don't bother?
Sure, you can still find the order. The order only depends on what the highest derivative is. So
Okay.
you could have something like, let's say a y times y prime, which now makes it nonlinear, but it's still first order.
Okay, what if I have like a y prime times a y triple prime?
Okay, so what if it's y prime times y triple prime, class? What order is it?
Same thing.
It's
4. I want to say it's 4, but
no, it's still going to be third order. Let me go ahead and draw it up on the board. So you're talking about something like that?
Yeah.
Right,
yeah.
Mikey? Okay.
It's written a little differently. They have it as like dy over dx and then d cubed y over dx cubed, but I'm pretty sure it's the same thing.
Yeah. So this is still third order.
Okay.
Because the highest derivative is the third.
Okay.
Okay. So in terms of order, linear, nonlinear, all you look for is what is the highest type of derivative.
Okay.
All right. Any other questions on homework stuff?
Yeah, sorry, a couple more questions.
Oh, that's quite all right.
As far as when it says find all solutions of the equation, so if we have like a y prime equals whatever minus x sine of x, essentially I'm just integrating that, and then all solutions would be with plus c, right?
Correct. Whenever it goes to what are all the solutions, we need to allow for that constant from integration wherever it plays out, because you're going to see, like, for the real basic ones, we always just put the plus c at the end and we're good.
Yeah.
But we're going to see with other, like today with some of the differential equations we solve, that c will end up being something more than just like a plus c. It'll get integrated into other things, but we always want to put that in to find all of the solutions, as opposed to a particular solution from an initial value problem.
Okay, I do feel like one of the homework problems had something like that, where I ended up having to do like a C1, C2, C3 kind of thing, because I had to integrate C a few times.
Right. Yeah, and that'll happen. Like a great example is the in physics, when you're given an acceleration, you integrate once, you get a constant in your velocity. You integrate again, you get another constant in your position. Right. So depending upon what order you have, right, the greater the order of the differential equation, the more constants that are going to pop up.
Okay.
So.
Cool.
Yeah, good question. Any other questions on homework? No? All right. Well, then we're going to go ahead and keep moving along, and we're actually going to start solving differential equations. We're going to start learning about the different processes. So I'm going to mute everybody real fast, just so, wrong button. So this way there won't be as much jumping around with the screens. It'll key in just on either me or the whiteboard, but please feel free to unmute yourself, right? Spacebar real quick, or just click the unmute button if you have any questions, all right? But we're gonna go ahead and actually start solving differential equations. And we're gonna start easy. Like I said, we're gonna primarily do linear stuff, but not always. We're going to be able to do things that aren't linear. But we're going to start with first order. We're going to start with first order differential equations. So all we're going to have is a y prime, no double prime, no triple prime, nothing like that. And we're going to start with the linear, but also work on approaches for things that are not. So let me go to the whiteboard. And let me start with just explaining what a linear first order is going to look like. So we're going to be able to always write a linear first order in the same kind of form. It's always going to be able to reduce down to something that looks like this. Y prime plus some function times y, and notice that this is a function of x or t or whatever our independent variable is. And then that's going to equal some other function of x. So if you can write a differential equation in this form, it's linear first order. So you see the linearness, and you can also see that it's first order. So that's what we're going to be working on, is solutions to these kind of guys. All right, now we're going to basically divide this into two smaller groups, some smaller subsets. The first is going to be homogeneous. And I know that we've probably heard this term in lots of places, but homogeneous, this is in the case of linear first order, this is going to be when that g of x, this guy over here, is equal to 0. Okay, so if we can write it in such a way that it's equal to 0, we call that homogeneous. Obviously, if it's not homogeneous, it's called non-homogeneous. And that's going to be the other case. So we're going to actually break this down. We're going to start by solving homogeneous ones, and then we'll move to the non-homogeneous because they're a little bit more complicated, just a little bit more complicated, but also we use the process of solving homogeneous to solve the non-homogeneous. All right, so the other thing that we have to realize is that the solutions are only going to be good in intervals where these guys P and G are continuous, right? Like you can imagine that, like, let's say this function was like tangent of x. Tangent of x isn't defined everywhere. And so if we go and we find a solution, the solution to this differential equation can't be defined somewhere where these individual functions are not. So hopefully that's kind of a no-brainer. Makes sense that we can only be in intervals where these things are continuous, but I do want to mention it because we're going to be looking at that a lot after we find our solutions. And one of the questions is going to be, over what intervals can we actually use it? And you should this should sort of bring back some memories of series. Remember when we did power series and stuff like that, we had to find the interval of convergence, which was basically, where is this even good? It's kind of the same idea. All right, so we're going to be looking for how we solve these guys. The simplest, most basic, most boring, not even going to talk about them after about a minute, are the ones where P of x is 0. Okay, so let's just look at that real quick. What happens if P of x is actually just the 0 function? It's identically 0.
Then
Well, that turns this differential equation, this linear first order, into y prime equals g of x, right? It's still linear first order. It's still written in the form. But you can probably see why I don't want to bother talking about these. Right?
That's just the derivative.
Yeah, this is what you did in Math 106. This is find the integral, right? So for this one, the solution literally is just the integral of g of x, and you use whatever technique you need, right? Parts or just straight integration, whatever. But that's why we're not going to bother with these. You already know how to do these. We're not going to waste our time. So let's turn our attention to those where P of x is not 0 and see how we're going to go about solving it. So let's go with homogeneous first. We're going to go with these guys that look like y prime plus P of x times y equals 0. All right. So let's think about how we're going to solve these, and let's even start with one that is kind of easy let's say P of X is constant. So let's look at this case first, all right, where P of X is a constant. And we'll do a specific number, just because I know that'll probably make you feel better. Let's say we have y prime plus 2y equals 0. All right, so let's think about how we might solve this. Do you remember seeing ones like this back in 106? Maybe 107, somewhere in there? Because these are the ones that the trick was to do this, where you just do a little bit of algebra, move that 2y over, you change this into a dy dx, and then you can like make sure all the y's are on one side and x's are on the other. Called that separation, right? So it's a separable equation, and we get dy over y equals minus 2x. So head nods, thumbs up. You kind of remember seeing these? Yeah, okay. Because now the trick is you just integrate both sides. And so we get the natural log of y equals, I don't know where that x should be a dx. So we get minus 2x plus c. And then to get y, all we had to do was swap it, change it into an exponential form. You get y equals e to the minus 2x plus c. And that c as an exponent, that became a multiple out front. And so the solution to this is actually a y equals c e to the minus 2x. So when p of x is constant, you always end up with an exponential function. And so you saw this when we hit exponential growth, that section in first year calculus. What we say is that the rate of change is proportional to the population. If this number right here is positive, then we had exponential growth. If it's negative, then we had exponential decay, right? But it was always e to that power. So we could even really generalize this if we just went to y prime plus ay equals 0. The solution is going to be c e to the minus ax. So that's awesome. We just took care of an entire class of linear first order homogeneous. If that p of x is constant, done. All right, so you probably, now that you've seen this again, it probably brings back the memories, and hopefully you recognize that, and it's nothing new. But the one other thing I wanted to mention is, what if this is an initial value problem? Like, what if we had been told, well, we do have a condition of y of 0 is equal to, let's just call it y naught. Do you remember where that showed up in the solution? You remember the pattern for C?
Wasn't that that your constant that was tagged onto it, right?
Yeah, this ends up being C itself, right? Like Wes just threw on the chat, he said we can just solve for C. It's like, yeah, you put 0 in for x, e to the 0 is equal to 1. 1 times C is C. So that C is actually equal to that initial y value. And that's another nice thing. That's another nice thing about this form, is that if it's an initial value that starts at 0, it's super, super easy. And you may remember this from like interest problems and things like exponential decay for half-lives and all that. We just throw the initial amount as our constant, and then we're good.
Because that was your principle if you're using it for compounding continuous.
Correct.
Yeah.
That's your PERT formula. All right. So no big deal. But again, I haven't really shown you anything new. You've already done this before. So let's make it new. Let's go to where px is not a constant. So an example of what I mean is something like, what if we had y prime plus 2x times y equals 0? All right, so the question is, can we do what we did before, which is basically shift stuff around so that they're separated so we can integrate? And this one you can see pretty clearly is that case, right? We get now minus 2xy. If you do the whole dy dx thing, we're going to get dy dx is equal to minus 2xy, which then brings us dy over y equals minus 2x dx. So again, it's separated. And at this point, we can integrate. So while it was a little bit more complicated in terms of form, right? Not just a constant, the process is the same. You go ahead and integrate those suckers, and you're going to get the natural log of y is equal to, in this case, minus x squared plus c. And then converting it to exponential form, running the hook, we get y is equal to e to the minus x squared plus c. And we'll go ahead and pull that c out front using the rules of exponents. So that was another one that was pretty quick, right? Because it was separable. But now hopefully you're thinking like a mathematician. Mathematicians are all about, okay, well, we did this once, it worked this way. We did a second time, it kind of worked out the same way. Does it always work this way? Does it matter what this function is, right? Is it possible to still go ahead and kind of follow the same process? Because notice what we did. In this case, we moved that 2x over, so we had the negative of it. We integrated, and then we slapped it on as a power of e. If you go back and you look at the one where it was constant, did the same thing, right? Where it was just 2, we moved it over, it was now minus 2. Well, we integrated that thing, minus 2x, and then took e to that power. So let's see what happens if we legit just leave it as px. So assuming nothing about this at all, other than it's not 0, let's see what happens. So we have y prime equals negative p of x times y. If we do that whole separation thing, we're going to get dy over y is equal to minus p of x dx. At this point, we can go ahead and integrate again. So we're going to get the natural log of y is equal to the negative integral of p of x. And then if we convert, right, we go to exponential form, we get y is equal to e to the negative integral of p of x. All right, so it turns out for any linear first order homogeneous, we've got it solved. There it is. So hopefully you're seeing the power here. Right, and that's kind of the whole point. And by this point, you guys are seeing it, I think, in math, where we go to things that we know, we try a couple, and if we see a pattern, we try to show that that pattern exists. And in this case, it definitely does. So there's an entire class of differential equations that we have now solved. And this is really how we're going to attack differential equations all the way through. After we get done talking about first orders, we're going to go to second orders. We go, well, how do we do second orders? And we're going to try a couple, and we're going to start seeing patterns, and we go, all right, maybe these patterns hold. Let's see what happens. We make it generic. Next thing you know, boom, here's our answer. And you know, like I was telling you last time, how I never took this class. I just kind of taught it to myself. You can kind of see why I was able to do that, because by that point I had seen enough math to understand this process of use the patterns, spot a pattern, prove it. this is all about patterns. And it's also why I call it monkey math, right? Because we're doing the same stupid thing every time. The only thing changes is what P is. All right, well, that just means I have to get a different integral. Oh, look, P is 1 over 1 plus x squared. I guess this time I get an inverse tangent, but that's really the only difference. All right, so let's try one more here before we move away from these homogeneous to the non-homogeneous. All right, so let's try this guy. Let's go x, y prime plus 2y equals 0. And you know what? Let's make this a initial value problem. Let's say that we know that y of 1 is equal to 2. And really the only thing that I did there by throwing on an initial value, it means there's going to be that one more step where we plug in and we actually calculate the c. All right, so you notice that this isn't very much different, but it is different. Is it still linear? I mean, it's not written the same way, right? I don't have y prime plus p of x because I've got that x times it. But it is still linear. What would make this non-linear is if this was a y, right? Like y times y prime. But it is linear. It's just I don't want an x on there because if I'm going to go to that whole integrate p and get the negative of it and raise e to that power, I have to be in the right starting form. But the right starting form is just only y prime. So this just requires an algebra step. We're going to divide everything by x. And so this is the same thing. However, there is one thing we have to worry about. What did I just do that we have to watch out for?
X can't be 0.
Yeah, we got to watch out for that division by 0, right? If x is actually equal to 0, now we've got a problem. Where at the beginning, could x equal 0? I mean, sure, it's stupid. It's a trivial thing because if x is equal to 0, we're looking for a function such that 2 times that function is equal to 0. Well, that function is the 0 function. So it is possible. It gives us kind of a, well, it's not possible with our initial value, but the differential equation itself would have been fine. But now we do have to worry about the fact that we've restricted the interval over which our solution is going to work. All right, well, but now it's business like usual. So we need to integrate p of x. So we're going to integrate 2 over x, which gives us 2 natural log of x. We need to make it negative, and then put my plus e, and then raise e to that power. So we're going to get y is equal to e to the negative 2 natural log of x plus c. But this one I want to do a little bit of work on just to make it a little bit nicer before we plug in the values, because we can simplify this a bit. Right? So that minus 2, remember your rules of logs, can come in as an exponent. And then the e and the natural log are going to cancel. So we end up getting y is equal to c over x squared. And there was a lot of algebra right there. So I just want to make sure that everybody's got it. Again, that minus 2 comes as a power. So we have x to the minus 2. That's our x squared that's at the bottom. This c, I've got e to the c is being multiplied because we're adding exponents. Well, e to the c is now another arbitrary constant, but boom, there it is. All right. So you notice that we get a solution, y is equal to c over x squared. You can check it, just like always. If you differentiate it put it back in here for the derivative, the original function. You'll see that it all works out. But notice that this also caught that issue with the interval. Remember when we did this, we divided by x. Like Mikey said, we can't have x equals 0. Well, you notice that that's still true about our equation over here. X cannot equal 0. And if you think about the domain of this, the domain of that is everywhere but x equals 0. So we could have an interval from 0 to infinity or minus infinity to 0. But either way, we're avoiding that problem spot. All right, we're going to go ahead and find C. And we'll do that just by plugging in our x and our y. So we're going to get 2 is equal to c over 1 squared. So c is equal to 2. All right, so we just found our solution. Let me go ahead and just write it up here real quick. We've got that y is equal to 2 over x squared. So it doesn't matter at all. If it's a linear first order, homogeneous, the process is always the same. You integrate the p, you make it negative, take e to that power, simplify if you can, and then plug in to find your c value if it's an initial value problem. But this one specifically, let's talk about which of the intervals we're good on. So like, where is this good? What x values does this solution or this function actually a solution to the differential equation? Let's see, Will just wrote everywhere except x equals 0. You guys like that? You should definitely like the not equal to 0. Well, it turns out that's not quite right. This is actually only going to be good from 0 to infinity. And I can see on some of your faces the, wait, what? So let's talk about this for a second. All right, so why is it only 0 to infinity? All right, so let's see. Wes just wrote, oh, because of the natural log of x. That has something to do with it, yeah. When you integrate 1 over y, 1 over x, something like that, I don't know if you remember, but the actual solution is the absolute value, natural log of the absolute value, which does allow for the negatives. That's why we can be on the other side. So sometimes you actually can use those numbers. I know I get lazy and I don't put it there. But the reason that we only get values from 0 to infinity is for the initial value. Go back and look at the initial value, right? What x do we know about? If you look at that guy, it was x equals 1,
Yeah.
right? So basically, here's how you have to think about it. We're going to start at 1. And we're going to just keep moving away from 1, because that was our initial value problem. We're going to draw this function. But as we're moving to the left, we get stopped at 0. We can't make that jump over 0 because the solution is only good if x is not equal to 0. Right? So it's basically saying, oh, no, you're fine as long as we don't have division by 0. And now we're trying to get to a place where we do division by 0, and we have to stop and say, no, this doesn't work because we assumed we weren't at 0. We're not going to allow that to happen. Okay, so your initial value is actually going to determine which of those intervals that you're in, if there's multiple intervals that you could have. If you go back and you look at the one that we did just before, right? The one that was y prime, it was the y prime plus 2xy, right? That one, there were no issues with division by 0 or anything. The p of x was defined everywhere. So that one, we got that function of e to the minus 2, or was it, oh yeah, e to the minus x squared. That's going to be good always for all x, so we don't have to worry about that. You only have to watch for this if there's something that causes a problem with continuity for P of X or G of X when we go to the non-homogeneous. So any questions about that? Does that kind of make sense? We feeling all right? And I promise you, you do a handful of these, like legit, only a handful of these non-homogeneous linear first order, you'll have the process down because it's always the same.
Real
Integrate
quick,
P.
Bruce.
Yeah, go ahead, Mike.
You were saying initial value given multiple intervals is what?
Okay, so if you have multiple intervals.
Intervals.
Yeah, no, it's okay. I want to say interviews too. If you have multiple intervals, like in this case, we have less than 0 and we have greater than 0. Right? So we have multiple intervals. If you have an initial value problem, the X value is going to tell you which of the intervals you're in because you need to be in the interval that contains that X. So like in this case, we needed whichever interval actually had the 1 in it, which is 0 to infinity. If our initial value had been something like y of -4 equals blah, 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 then we would have been in the other one, the minus infinity to 0. All right, cool.
Perfect.
Other questions? All right, well, then let's go ahead and move to the non-homogeneous because this is where it gets more interesting and more applicable, right? Like the homogeneous, how often are you going to run into this exact form that is equal to 0? Not a lot. I mean, how often are you going to run into a linear first order? That actually happens considerably. But to get exactly this one condition, yeah, not very common. So let's turn our attention to what if it's non-homogeneous. All right, so in this case, now what we're going to have is a g of x that's not equal to 0. So we'll have y prime plus p of x times y is equal to g of x. All right, so how are we going to get this? Well, we're going to use a great trick that happens a lot in differential equations, and we're going to introduce what we call an integrating factor. So think about this. If it was equal to 0, if it was homogeneous, we could find the solution. We know how to do that, right? We just did it. Let's say that y1, that this is a solution to the homogeneous. We know we can find it. So let's just say, okay, y1 is this guy. Now, what we're going to do is we're going to make a guess. And we're going to guess that the solution is this form. It's going to be some function u, I don't know what it is, times that y1. All right. So basically the thought here is that we don't know what the function is, but it's going to be a multiple of that y1 because anything can be a multiple of it, right? I just have to multiply by the right thing. So we're going to try this form. I know. You look at that and you go, where the hell did this come from? This is one of those many miracle step kind of things where when you just look at it, you go, it's a miracle. But it came from the investigation of trying to solve these things, right? You go back a couple hundred years when this was brand new and people were slaving over trying to figure out the process. This is one of the things they tried. They're like, well, what if we try this? It turns out it's a method that works really, really well, where you take something that you know is an answer and you multiply by something else and see what the form is. And I'll go ahead and show you why this works, right? I'll show you why, or how we find out what this U is and why it's going to work. But for right now, I know it feels a little unsettling. You're like, what is this U thing? Just trust me, and you'll see. All right, so let's go to the board and let me show you why we're going to go with this form.
So if we're of this form, I'm not going to use the x's. I want to simplify stuff. If y is equal to u times y1, let's look at what y prime is going to equal. So to differentiate this, we're going to have to use the product rule. We've got two things that are being multiplied together. So we're going to get u prime times y1 plus u times y1 prime. So if we choose that form, that's what the derivative is. Here we go. All right, now let's put those back into the original differential equation. So what we're going to get, we're going to have y prime. So that's our u prime times y1 plus u times y1 prime. We're going to add to that p times y. Do it this way, p times, well, the guess we're using for y is u times y1. And that's still going to equal g. Well, check this out. If I factor out those u's, I'm going to get u times y1 prime plus p times y1. And notice that that right there is actually the form of our differential equation, right? It's y prime plus p times y. It's y1. And you remember what we know about y1? You look right here, right? y1, it was the solution to the homogeneous. What happens to this when I plug in y1? What does homogeneous mean again? It equals 0, right? So this right there, that's all going to equal 0. Y prime plus p times y, that's going to equal 0 when we plug in y1, because it was a solution to the homogeneous. All right, so that all goes away. And what we're left with, and I apologize that I don't have more space, but what we're left with, if we look at that, let me just bring this up top here. We're going to get u prime times y1 is equal to g. And now if we want to find u, this is easy. This is easy because y1 is a function. It's no longer y. It's a function that we know. So we get u prime is equal to g of x over y1, which means u is just going to be the integral of that. So if you've been paying attention, this is where you should be a little bit happy. I know that we get kind of lost in the weeds.
But the reason you should be kind of happy is that we were looking for a function that worked, and we are going with that guess, u times y1. Because y1 we knew we can get. Well, we just figured out how to find that u, which means we just found our solution. The solution is going to be whatever this is that we just calculate, this integral, times the solution to our homogeneous.
So I'm bringing you back to the board, and just so you can see what we're going to get then as our solution. Remember here where we said guess the solution is u times y1. that's what we're going to get. Our solution then is going to be y equals y1 times the integral of g of x over y1 dx. All right, so believe it or not, we just solved every single linear first order differential equation. All right, thanks, Brandon. I appreciate that. He just gave me a big fist bump, pumping his arm. I know it feels ugly, and we did all kinds of stuff, but we did it one time, and now we know how to get anything. All right, so before we jump to a couple of examples, any questions? I know we also might be at that point where we don't know what question to ask if we do have a question. But there's our derivation. Okay, so put this in a box. This is what we're going to want because this is how we're going to go about it. Now, it does require that we know y1, which means we're going to have to do that first step, right? We're going to have to solve the homogeneous. But then once we got the homogeneous, we can move on and find the solution to the non-homogeneous. All right, so we're going to start with sort of an easier one. And what makes these easy or not easy is usually the p function, not the g function. So let's look at this guy. Let's go with y prime minus 2y equals 3 e to the x. So let's try to solve this bad boy. All right, so the first thing that we always have to do, we always have to start with the solution to the homogeneous. So let's just think about this guy. Right, let's think about the homogeneous. This is one that we can get it super easy. Right, what's the solution to this?
Y squared plus c.
Yeah. So this is the good old y prime equals 2y. So if we do our separation and all that, we're going to get y1 is equal to ce
So
to the
2x, yeah.
exponential. So for these, when it's a constant, just change the sign and then make that the exponent. All right. Now, when we did the derivation for finding the solution to the homogeneous or the non-homogeneous, I apologize. You notice I just said that y1 is a solution. This is the list of all the solutions. All I need to do is pick one of them. Basically, that just means choose a value for c. Don't pick 0s. Right? So, because 0 is just going to give us the trivial solution, and that's not going to help us because 0 times anything is still 0. But I saw Ian just give me the finger, but this finger, right? Let's use c equals 1. So I'm going to pick y1 equaling just plain old e to the 2x. Since it doesn't matter, this is going to make all the calculations easier. You don't like that? Use 3e to the 2x minus 7e to the 2x, pi squared e to the 2x, doesn't matter. All right, so now we got to find our u. So if you go back and you look at how we found u, that's going to be the integral of the g of x, so that's 3e to the x, divided by y1. Actually, let me write it down. So this is g of x divided by y1. So we've got 3e to the x over e to the 2x. So this is the u we're going to use. All right, well, to calculate that, we're just going to do some algebra real fast. So we're going to get 3 e to the minus x. I'm getting really sloppy. I apologize. I'm not putting my dx's. But now let's integrate. Well, you got to like this. This is super nice. Exponential functions just give us themselves. We do have to use the chain rule, but we're going to get minus 3e to the minus x plus c. So let's just take a moment. Let's pause and think about what we're doing here. So we started by getting the homogeneous. We found a solution to that homogeneous. Then we use that solution to find this u. And we're just using the formula that we know works because we derived it generically. Okay, so now we've got our u, which means it's time to find our y. So our solution, remember what it was, it's u times y1. So we're going to have minus 3e to the minus x plus c times y1. And y1 was the solution to the homogeneous, which is e to the 2x. So I'm going to write the answer up here, clear some space. And so what we find is that the solution to this differential equation, and this is a list of all the solutions, it's minus 3e to the x plus c e to the 2x. And I just found this by distributing the e to the 2x through. Whew. All right, lots of steps, right? There are definitely a lot of steps, but it's procedural. It's the same thing every time. All right, so we can actually have that same discussion of where is this good? Well, if you look at the original function, the p was minus 2. Well, that's defined everywhere. 3e to the x, that's defined everywhere. So we know that this is actually going to work for all x. And if we are given an initial value problem, that would allow us to find the c. But regardless, the solutions all look like this. All right, your faces don't show enough impressed, right? I don't know if you see the power of what we just did, right?
We just did it one time. And that's all we ever have to do because it's the same thing over and over. Just choose a different P. Now we got a different G. Whatever, right? It's the same process, which for some people really like this. You got your recipe, you just do it. Me, not so much, right? You guys already know how I feel about monkey math. That's one of the reasons why I quit doing science, is because all they wanted me to do is this kind of stuff. It's not creative. I mean, we use the creativity to get that first step, but then after that, it's just same thing again. Different P, but same thing, right? But don't let that discourage you. I know as soon as I start talking like that, sometimes you guys all go, that's just me. But for those of you that like having those recipes, you're going to love this stuff because it's just the same thing over and over and over. So you practice it and you'll eventually get good. So let's do another one. Let's make it a little bit more complicated in terms of the steps. But you're going to see that the process is exactly the same, okay?
All right. So this one, I know I'm going to way run out of board. So if you end up missing something, I will do my best to go back and recreate it. But if not, watch the video again and you'll be able to see it. All right, so let's look at this guy. Let's go with xy prime plus x plus 1 times y is equal to x. And you know what? Why not? Let's make this an initial value problem. Let's go with, we know y of 1 is equal to 1. So we're going to look for the individual, the specific one that actually goes through the point 1. All right, so here's our process. Start with solve the homogeneous. Then use that solution to the homogeneous to find your u. Multiply that u to that homogeneous solution. And there we go. All right, so let's start with homogeneous. But before I even try that, I need to do an algebra step. Right? We just like that other one where we've got the x times y prime. We need to go ahead and divide by the x. So we're going to get y prime plus x plus 1 over x times y is equal to 1. So that's the form that we are used to. So let's go ahead and make it look like that again. All right, so let's go to the homogeneous. So we're going to take y prime plus x plus 1 over xy equals 0. So remember what we do. We take p of x, we integrate it, then we make it negative, and then we take e to that power. All right, so we got to integrate this thing. Probably easiest if we just separate it. X over x is 1, 1 over x is 1 over x. This is going to give us e to the negative integral of 1 plus 1 over x, which is going to be e to the minus x plus natural log of x. And again, remember we have a plus c. But since we're just trying to find y1, we can pick c to be anything. In this case, I would definitely pick c equals 0, because then adding it, it goes away. So we end up with e to the minus x minus natural log of x. And if we kind of split this apart, the fact subtraction drops it in the denominator, the e to the natural log cancels. We get y1 is equal to 1 over x e to the x. So any questions on y1? And again, this is just the y1 that I chose. You can choose anything you want. Let that c be any number. I don't care. So since you have choices, pick whatever makes this easiest. Okay. All right, so there's a solution to the homogeneous, which is great. But yeah, we still got a lot to go, right? So let me go ahead and rewrite this up here. I'm gonna write it up here, sort of use this to keep track of where we are. All right, so that box, that was our original differential equation with the initial value problem. And we just calculated the y1 that we want to use is 1 over x e to the x. All right, so now we find u. So again, the process for u, it's the same every time. We're going to integrate the g of x. Oh, shoot, I just erased that one. What was the g of x here? Be careful.
Wait.
It's x.
X? Right. Yeah, it's right up in the.
All right, so Wes just threw in the in the chat. He said 1, since we divided by x, and then I think he was admonishing you all, saying no, 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 no. Right? It's not x. It's actually 1, because remember the first thing we had to do was divide by the x. So if you look at the bit that I erased, you go back and look at your notes, where it was y prime plus x plus 1 over x times y, it was equal to 1. So our g of x is 1. And we're dividing by y1. So this actually brings me to a place that I want to pause and warn you about something. While this is really procedural, it's nice you just do the same thing over and over and over.
You muted yourself.
Fine, I'll come back and I'll talk to you again. Sorry about that. No, I can't stress organization enough here. And I know that probably sounds funny because you guys know how unorganized I am in daily life. But when it comes to this, write everything down. Make sure that you know, when you do those steps, what I would recommend is maybe put a box around the differential equation when it's in the form y prime plus. Once you calculate your y1, put a box around that. Once you calculate your u, put a box around that, just so that you can easily find that information and put them back together. But I think you guys can see how you might run into some trouble here with everything everywhere. And be ready to use a lot of paper. These problems are not going to be two-liners. All right, so let's come back to this. So here's our u. So we need to do this integral. Obviously, we can just flip that thing over, and so we're integrating x e to the x. If you're going to do this the long way, this is going to be an integration by parts. Obviously, I know you guys are going to use something like, you know, some magical technology that does everything for you. And yes,
Not me, Bruce.
You did hear that disgust in my voice. And yes, Mikey, I do know that you're going to be good about that. So we integrate this. If you did integration by parts, you'd let u equal x, dv equal e to the x. But what the integral ends up being here, we calculate this, we get x e to the x minus e to the x plus c. Yeah, so if you look in the chat, Wes just gave you the steps for integration by parts. He's showing off again. All right, so there's our u. So now let's go back to what the process is here. We take that u and we multiply it to the y1. So that means our solution then is going to be x e to the x minus e to the x plus c. And we're going to multiply that by y1. And what we end up with is 1 minus 1 over x plus c over x e to the x. And so there's the list of all of the solutions. Every solution to this differential equation has this form. But of course, we had an initial value problem, which means we need to go ahead and take this y1 equals 1 and put that in here to find c. So let's just bang that out real quick. So x is 1, y is 1. So we have 1 equals 1 minus 1 plus c over e, which makes c equal e. So we go ahead and we put that back in. And I'll write it up here at the top again. We've got y equals 1 minus 1 over x plus e over x e to the x. But you'll never see it written that way. You'll go ahead and use the rules of exponents. And if you take that e and cancel it out, put a box around it. But there it is. There is the function that satisfies that original differential equation that passes through the point 1, 1. But you can check it. You can go ahead and plug that back in, right? Take its derivative, multiply by x, and blah, 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 blah. And it will work out, assuming we didn't make any mistake along the way. Whew.
All right. So how do you feel? Do you feel mind numb now? At least it's straightforward. It's same process every time. And I promise you do a few of these, you'll get it down, and you won't really have to think about it anymore. You'll just turn on autopilot and do them. But there you go. You have now solved every single linear first order differential equation. Not bad for a day's work, right? So that's kind of nice. However, there are lots of other differential equations, and we do still need to talk about, when are we guaranteed solutions? Like, are we guaranteed solutions? I showed you ones that worked, right? I mean, we found them. Are we guaranteed that we're going to find solutions? So I don't know if you guys can see everybody's screen. Wes is shaking his head no. Ian's giving me the head no with a little bit of maybe not on the face. Right? And so that's a legit question. Like, yes, we did this process and it worked. And when I said, hey, let's do it generically, and we just kind of busted through it, yeah, everything's great. But there definitely are some issues. First and foremost, think about when we went and we tried to solve either for the homogeneous or non-homogeneous. Just start with the homogeneous part. We had to have a function that we could integrate. And that's not always going to be the case, right? Like, think about a real simple one that would be an issue. I'm going to go ahead and write one on the board here real quick.
Like, what if I gave you y prime plus e to the x squared y equals 0? So homogeneous, first order, no big deal, right? And the way that we solve this is we have to start by taking the p, e to the x squared. We're going to integrate it, make it negative, and then take e raised to that power. And you all know, because this is one of the classics, that this is one that is not possible to integrate. Okay, now, does that mean that there's not a solution?
Well, this is where we got to be kind of careful, because just because it's something that we can't compute doesn't mean that it's not a solution. There is a solution, and it's what I just wrote on the board there, e to the negative integral of e to the x squared dx. Yes, you're not going to be able to write that down as a specific function like inverse tangent or natural log or anything like that, but it does exist. Right?
Is this where power series kicks in?
So the power series stuff would definitely kick in here, Thea, when we have initial value problems.
Got it.
And that's going to be more the case when it's u that we have trouble finding. Because remember, there's another place where we have integrals too. Like, there's for the p, but even if it's a homogeneous that we can solve, and yeah, we get it, we then take that solution and do the whole divided into the g and blah, 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 right? That integral also might have a problem. If it's that second one that has the problem, the u, that's where power series can be much more useful, especially if it's an initial value problem, because then you can just approximate it with however many terms in the power series as far as you want it to go, and you can get an approximate solution that's going to be good for a small window, right? Like wherever we're centered, as long as we're in a small window about that, we're pretty much assured that that will be a good solution. You know, if you go back, remember when we were doing the slope fields and we're drawing the approximations, it'd be like, well, we know what's going on right here in this slope field. I don't really know what's going out far away, but I can trust myself if I'm kind of close. So yeah,
Because
there's
power
one of those.
series is like only accurate within a certain portion interval without having to go out tons upon tons upon tons of terms in the power series, right?
Right. And we saw that, I mean, in terms of just where that power series actually is equal to the function, that's what the interval of convergence told us, right? That's the domain. But then as soon as we start, you know, cutting off terms and we're approximating, we also, I mean, I don't know if you remember, but there was a way for us to look and see how we knew our tolerance, basically. We knew how far off we were. We're always off by at most, well, it depends what kind of power series you got, but like with the alternating series, for example, we're off by at most that next one.
Yeah.
Right. But so yeah, there's some built-in how good is our approximation when we're dealing with power series, and that would definitely come about here if we were using this for something in the real world.
Got it.
Where sure, writing it as the integral of e to the x squared is fine to a mathematician, but to the scientist, and I don't have my hat to turn backwards, but the scientist is going to go, yeah, I don't want e to the x squared, I need a number. And that's where the power series happens. So that's one of those things that is going to happen with these, is that you might get integrals you cannot do, but it doesn't necessarily mean that there's not a solution. And in the future sections, we're going to talk about, it's called the existence and uniqueness theorem. Existence, does a solution exist? When does a solution exist? Uniqueness, is there only one, right? Or one group, one class? Like when I did this, remember how I was saying, well, we just found all of the solutions. They're of this form with the C, and none of you question that. I think I've trained you well enough that you're just like, ah, Bruce says it, it must be right. Fools. Now, but you just sort of, yeah, okay, why not? But obviously mathematicians are always like, well, yeah, we found solutions. Like what we did does find us solutions, but are there maybe some that don't have that form? Well, we'll talk about with differential equations, and this is common with differential equations, is not just existence, but uniqueness. Are we, when we do this process, are we finding the one and only one? So we will talk about that later when we get there. But I think we're good for today. I know we've got a bit of time left, but I don't really see the need to make you guys sit through another example because it's just going to be the same thing. I think it'll be better for you to practice it yourself. So I'm going to go ahead and stop the recording.